Hello, am I audible? Hello. Okay. I will wait 1 or 2 more minutes because I see only 40 students are in the class. Okay. So in our last lecture, we had already gone through IEEE 802.3, 4, 5, etc. Okay. And we saw different types of protocols, that is token bus, token ring, then CSMACD, CSMACA, etc. All these things we have discussed. Okay, and those were used for the local area networks. Now we'll see, we'll broad our thing. We'll go through the metropolitan area network, in which the number of hosts would be more, as well as the distance between the host would be bit it would be greater. It is not restricted only to a certain region, but it would be it is laid within the entire city or something like that. Okay, so the standard what is meant for this, uh, I didn't get what he wants to tell. Madam, in will token be passed through hub? It is not 802.5 is a token ring. Fine. So from one station to the other station, the token would be circulated.
Hello, ma'am. Ma'am, in IEEE 802.5, we are using star topology. So, will the token go through the hub or from like A to B, or it will go through the logical ring that is created in that?
Through, star topology, no doubt. It is like for that you are having one, one is for sending, the other link is for receiving. Every station would have two links. Are you getting me? Okay. It is something like you are connecting all these devices through this hub. So say suppose A wants to send, pass on the token to B, then through hub it is passing. That's all. Are you getting me? Okay. Right. Okay. So in this, it uses distributed DQDB. The protocol is known as DQDB, which is nothing but distributed queue dual data bus. Distributed queue dual bus. DQDB stands for distributed queue dual bus, and the interface is known as distributed queue data interface. Now, every host in this metropolitan area network, or you can say 802.6, they are having two buses which are laid like this. So you can see that there is two buses, bus A as well as bus B. There are two buses which are laid, and all these computers are interconnected or are connected to both of these buses. Fine. And every host or every station should know which are the stations to its right and which are the stations to its left. Are you getting me? So 2 should know that station 3 as well as station 4 is towards its right and station 1 is towards its left. Are you getting me? Okay, the position of the host should be known, the position of other hosts should be known by each of the host or each of the station. Followed? Now, this you can see that this is some square which is shown here. This is nothing but the head end. It is known as head end. So this is your head end. Okay. Here also. So two head ends would be here there for two buses, bus A as well as bus B. Fine. Now this head end, it would provide a 53 byte cell, a 53 byte cell is nothing but the frame. 53 byte frame is generated, and it would pass that 53 byte frame through this in this direction of the bus. Similarly, this also would generate a 53 byte cell, and it would send in the other direction. Follow? Now in this 53 byte cell, there would be a 44 byte payload field. Among this 53 byte, 44 byte would be the payload field, and there are two bits apart from this 44 byte payload field. One is known as the request bit, the other one is known as a busy bit. Are you getting this? So the head end would generate a 53 byte cell. Whoever wants to send the data, then they can put their data into this 44 byte payload field. And apart from this 44 byte payload field, there are two more bits into the header of this, or the remaining bytes, whatever we are having. Among them, two more bits are there, which is known as a request bit as well as the busy bit. Understood? So two more bits are there. Say suppose any station wants to send certain data to, say suppose 3 wants to send some data to this 1. Okay, and 3 knows, as I said, every station should know who are what is the where are the other stations, like whether it is towards its right or towards its left. Now if a station 3 wants to send some data to station 1, so what it will do, the actually the station is in this direction, isn't it, from 3 to 1. So what it has to do, it has to use this bus, that is bus A. In that bus A, in this 53 byte cell, it has to set the busy bit. Sorry, it has to set the request bit. Okay, it has to set the request bit. So when this cell is moving through this channel, all the stations which are after this station 3 would come to know that station 3 is some station on the other end, on the other hand, they are requesting. Are you getting this? And once they use the station, once they put their data onto this payload field of this cell, they will make again on the same again on the same bus for the other frame, they may set this busy bit, say which indicates that now the frame has been provided into the payload field of this bus. Okay, so we'll see how it works. For example, say suppose and it maintains two counters. One is known as RC, that is known as a request counter. So this is known as a request counter, and this, the other counter is also known as CD. CD is nothing but the countdown counter. Two counters are maintained. One is known as a request counter. The other one is known as a countdown counter. Now what happens, and it maintains the order of data which can be provided by this stations, or which can the order in which they have requested it is served in the FIFO order, that is first in first out order. Now we'll see how this FIFO is maintained using these two counters, that is request counter as well as a CD, that is countdown counter. Now assume that you can see that initially all this request counter and the CD, that is countdown counter, all of them are initialized to zeros. Okay. Now assume that station D wants to send certain data towards its right hand side, okay, to some station which is at the right hand side. So what it will do, it will send it into the frame cell which is sent by this head end towards in this direction. As I said, into that frame, we have one bit which is known as a request bit. So since station D is ready with certain data which has to be transmitted, so before actually its turn come, what it will do, it will set that request bit which is moving, which that cell is moving from this bus. Are you getting this? Through this head end, the cell of 53 byte would be continuously transmitted through this bus. Similarly, this head end of this also would be continuously transmitting a 53 byte cell. And among this 53 byte cell, we have one is the request bit, the other one is the busy bit. Now, since D is ready with certain data and it wants to send certain data onto the bus which is at this in this direction. So for that, it has to send a request. First, it has to send a request, set the request bit. So among this 53 byte cell, which has the request bit, it would set that particular bit of that particular cell. Are you getting this? So when that 53 byte cell is moving in this direction, all these stations would sense this request bit, and what they'll do, they'll request counter is incremented by 1. Are you getting my point? Hello? D wants to send a frame. Okay, it has to send some data in this direction. Say suppose there is some station, say E is there. It wants to send some data to the station E. Are you getting this? So which is in this direction. So what it has to do, it has to use the opposite direction bus. In that, the 53 byte cell, which is continuously it is transmitted by this head end. So when it reaches here, the request bit of that particular cell should be set to 1. Okay, so all these stations are sensing that request bit, and they'll come to know that some station towards this right hand side is requesting for the for its turn. So what they'll do, the request counter would be incremented by 1. Is it clear now? You can see that this is also 1, this is also 1, and this is 1. Hello. Say suppose again E also wants to send certain frame. So what happens? Again, it would also set that request bit of the next frame which is coming in this direction. So what, this would also be incremented by 1. This would become 2. This would become 2. This would also become 2. Is this thing clear, everyone? Hello. Fine. Among this 53 byte cell, 44 byte would be the payload field, and 1 bit is among that the remaining bits. 1 bit is request bit, the other bit is busy bit. Okay, so if anyone wants to transfer or wants to use this frame, wants to put their payload field into put the data onto the payload field of that cell, they will send a request bit. You can see that this is a request bit. They'll set the request bit of a frame cell which is moving in this direction. Okay, so all the stations may sense that, and they'll increment the request counter by 1. Is this thing clear at least now? What does this indicate? That towards the right hand side, some station wants to transfer the data. Is it clear now? Hello? Fine. Now what happens? Say suppose station B also wants to transmit. Station D was wanted to transmit, so it has sent a request bit. Just it has just see D wants to send some packet in the or some data in this right hand side direction. So it has to send the request bit in the left hand side. Are you getting this? If D wants to send to C, then it should be in the opposite direction. Then the request bit would be in this direction. Is it clear, Priyank? Fine. Now, in case, say, suppose after D, B also wants to transmit. Fine. So what it will do? A request would be sent. A request bit would be set by the station B also. So when B is ready with certain data and when it is sending a request bit, whatever B was there in the RC counter, that would be copied into the CD. Are you getting this? That would be copied. So one earlier here it was 1. So now it is copied to CD and that RC would be set to 0. That request counter would be set to 0. And since this request bit is moving in this direction, the station A would find it. It would find that earlier it was 1. Now one more request has come, so the counter would be incremented by 1. So it would become 2 now. Is it clear now? Hello. So what does this indicate? Let me tell you. Okay. So this indicates for station C, what it indicates that there is some station towards the right hand side which has requested when a station wants to transmit or use the channel, and when it is sending a request, at that time the request counter value would be copied to the CD, that is countdown counter. Okay. So what does this indicate is that C comes to know that before there is one station which has already requested, which is towards its right. Okay. Whereas when this RC is equal to 0 and CD equal to 1. So what does this what does this indicate for that? That before my turn, because here RC is equal to 0 and CD is equal to 1. Before my turn, there is one station which has already requested. And whereas here, what does it indicates? There are 2 such stations which has requested or which has already requested. Is it clear? Now say suppose once now since D has requested first, are you getting this? So that frame cell which is sent by this head end, it would be moving through this. So RC station A would find that there are 2 requests, so it would not put its data, A's data would not be put into the payload field of that frame cell. Again, the frame cell would be moving through this direction. Now when it reaches to B, what it finds that this RC is equal to 0, but CD is equal to 1. That means before my request, one station has already requested. Okay. So it would not put its payload data into the payload field of that. Again, when that frame moves to this station C, again here it is 1. It indicates that one of the station has already requested. So when it reaches to D, so since it is 0, 0, that means no one has requested. So what it will do, it will put its data into the payload field of that frame cell. Okay. And what it will do, the busy bit of the frame cell which is moving in this direction, in the other direction, so that will be set to 1. Okay. So when the busy bit is set to 1, what it will do? So see here, the data is sent here and the busy bit would be set to 1. When the busy is set to 1, the request counter of this would be decremented. Now here also the CD value would also be decremented, whereas now here you can see that earlier it was 2, now it has become 1. That means there is one more station towards the right hand side which wants to access that channel. Okay. So now after this, again when the frame cell comes, it would see that B would see that the CD value is 0 now. That means no other stations in this direction are access wants to is has not requested before myself. So what it will do, it will put its data into the payload field of that 53 byte cell, and the busy bit would be set to 1. And when the busy bit reaches here, it will what it will do, it will decrement the count by 1 and it would make it 0. Is this thing clear? So you can see that how the FIFO order would be maintained by using these two counters, the request counter as well as the countdown counter. Okay. Say suppose if RC value is equal to 3 and CD is equal to say 4. What does it indicate? Say suppose station 3's RC value is 3 and CD value is 4. What does this indicate? Three station towards right want to transmit. CD is equal to 4. When this RC value would be copied to CD, that means before myself there are 4 stations which wants to which has already sent a request. Is it clear? You can see here. This is what we have done. Earlier here RC was 1. When the station B became ready, 1 RC's value is copied to CD. Isn't it? So if RC is equal to 3 and CD is equal to 4. CD is equal to 4 means what? Before myself, there are 4 stations. Yes. Yes, Prince. It's right. Okay. 4 stations have already requested. So it should not catch hold of the 4 frame cells which are moving. Okay. And then when this becomes 0, CD becomes 0, it implies that now it's done. After it's done, there are 3 more stations which wants to access the which wants to put the data onto the bus. Is it clear? Hello. How about others? Partially clear. Shall I repeat it once again? Hello. Do you want me to explain it once again? Or is it fine? See, I will take the same example. Say suppose first station D wants to send. Initially all of them are zeros, request counter and countdown counter. Okay. And head end would continuously send the frame cells 50 of 53 byte. Whoever wants to transmit in the payload field of this 53 byte, they have to copy their data. Fine. Now say suppose D wants to send certain data on towards this direction. So it has to send a request in the opposite direction. Is it clear? At least, because as I told that every station should know which are the stations towards its right and which are the station towards its left. Fine. Now say suppose station D wants to send certain data to a station which is towards its right. It has to send a request towards its left. So when the request bit is sensed by all these all these stations, they will make their count. They'll increment the request counter by 1. Okay. So here you can see earlier it was 0. Now it has become 1. Now after this, station B also wants to send the data. So even it has set the request bit 1. Okay. So since you can see that the request counter of station A has been incremented because only this has sensed it, whereas here they haven't sensed it, isn't it? So the request counter has been incremented by 1, so it is equal to 2 now. Okay. Now, once it has been done, aha, and what when is having its data to be sent, when it is sending a request onto this bus, the current value of RC is copied into the CD and RC is initialized to 0. So what does this indicate? That before my turn there is one station which has already requested. The CD value indicates that, whereas RC value, what it indicates, that after my turn how many stations are there which has requested. Is it clear now? Okay. So now you can see that station D has used that channel, and it has sent the data. So once it has sent the data, the busy bit would be set to 1. When these stations would sense the busy bit, the RC value would be decremented by 1. So this has become 0. The CD value of this would be decremented by 1. So this has become 0. Whereas RC value of this is also decremented by 1. It was 2 now, that has become now 1. Fine. Now, when once more this B would that 53 byte frame would move through this channel, since B is having this 0 0, that means it is now its own turn. So it would put its data into the payload field, and what the busy bit would be set to 1, and it would be moving through this channel. So when the busy bit is sensed by this station A, what it will do? It will decrement this RC value by 1, and now it has become 0. Is it clear now? Hello. Fine. This is how the 802.6, the metropolitan area network, would work. Fine. Now, so some technical details of this DQDB is it can operate up to distance of 200 kilometers, up to distance of 200 kilometers, and it uses either the this channels are made up of either copper or optical fiber. Optical fiber cables can also be used. Okay, so these are some of the features of 802.6, that is metropolitan area network. Okay, and it can be designed for transmitting both the video as well as the both the audio as well as video data. When data is, yes, when data, once it is transmitted by any of the station, it has to send that busy bit. It has to set the busy bit. Is it clear? By looking at the busy bit, the RC value would be decremented by these stations. The request counter value would be decremented by 1. Hope this is clear. Okay, this is how the FIFO, that is first in first out, is maintained using these two counters in this 802.6 protocol. Hope everyone is clear with this. Any doubts? Fine. Then next we'll see IEEE 802.2 logical link control. Okay, so till now we have in the last chapter, I mean in the third chapter, you might have studied about the data link layer, in which you have studied about the error control, flow control using the sliding window protocols, etc. Isn't it? Whereas whatever we have studied in this chapter, okay, that is a max sublayer, in which we have least bothered about this error control or flow control. For example, Ethernet, if we are using, we don't say anything about this error control and flow control in case of Ethernet, isn't it? So the Ethernet or any 802 protocols, it just offers a best effort service. Best effort. That means it tries to provide a best service, but every time it is not necessary that it succeeds. Are you getting this? Okay. It provides the best effort datagram service. Now, sometimes it is fine that if some of the packets which are coming from the network layer. If it is lost, then it is fine. If it is if we are talking about the connectionless service or UDP, because there is no such error control or flow control in that case, then it is fine. But in some protocols it is necessary that it has to follow this error control and flow control. But the Mac protocols, whatever we have studied, it nowhere it supports this error control and flow control. That is 802.3, 4, 5, etc. Whatever we have studied till now. Fine. So one more, this data link layer, you can see that it is divided into two sublayers. One is the MAC sublayer, the other one is the logical link control sublayer. Okay, so this LLC, which is also known as a logical link control, and there are certain uh, some standards have been provided by this IEEE, and the standards are known as IEEE 802.2. Fine. So in this, the packet the packet which is sent by this network layer on the sender side through the LLC access primitive, it would provide this packet to this logical link control sublayer. Okay. Now this LLC sublayer, it would provide its own header. Okay. And this header contains the sequence number as well as the acknowledgement number. By using this, it tries to control, it tries to follow this error control and flow control. Are you getting me? In the Mac sublayer, you don't find the error control or the flow control, but by using this LLC sublayer, okay, in its header, it has some sequence number as well as the acknowledgement number of the fragment or the packet, okay, and you can see that the entire packet with this LLC header, okay, that forms the payload field of this MAC sublayer, and that is provided into the frame of this either the Ethernet or token ring or token bus, etc. And since we are using different types of uh, protocols like 802.3, 4, 5, etc., all these are having different frame structure. They don't have the same type of frame structure. You might have seen frame structure of 802.3, that is Ethernet. Okay, but the frame structure which is meant for Ethernet may not be same for 802.4. It may not be same for 802.5 and so on. Okay, so at the if say suppose you are having different frame structure, then it would be very difficult to at the receiving end to where to find the source address, where to find the destination address, etc. And for the network layer, it should be same, isn't it? It should not to make out what would be the frame structure. Okay, either it is using IEEE 802.345, whatever it might be. For the network layer or for the higher layers, it should be made transparent whatever the underlying protocols you are using. Is it clear? Okay, so that's why the LLC, that is a logical link control layer, came into the picture. Fine. So this LLC it provides three different types of service. One is known as unreliable datagram service. In this case, if the say suppose if the packet is lost or if the frame is lost, no, it doesn't bother. Or it can be acknowledgement or acknowledged datagram service. That means uh, a timer can be set if in that by the sender. If it does not receive the acknowledgement from the receiver, then it may do some task like resending the frame, etc. And the third type of service which is provided by this LLC is the reliable connection oriented service. Connection oriented service. Hope understood why we are using this LLC. to provide the error control and flow control, and to make the upper layer transparent of whatever the type of protocol or type of the standards whatever we are using, because different frame format, different these standards protocols are having different types of frame format. Okay, so the higher layer should be transparent about it. So that is why we are using this LLC, that is logical link control. Okay, so this LLC header, it contains three fields: a destination access point, a source access point, and a control field. So this access point is nothing but, because every host, okay, so there might be number of processes which are running in this host, isn't it? So access point refers to among these number of processes, which is it would provide the process, which process this particular frame belongs to. Okay, so that is nothing but the access point. So the destination access point, that means destination process number as well as the source process number, can be provided with this field, okay, which is embedded into this header of this LLC. Okay, whereas a control field contains the sequence number as well as the acknowledgement number. Hope this is clear. What is the role of the LLC, or the logical link control? Hello. Right. So till now we have learned about the wired type of network. Next we'll see about the wireless LANs. Okay. That is the standard which is used for this wireless LAN, like Wi-Fi, etc. They are using this 802.11. These are the standard which is used for the wireless LAN. Okay. Now this 802 this wireless LAN can be operated in it can operate in one of the two configurations. There are two configurations which is provided. One of them is known as the configuration with a base station. Okay, that means there would be some central control would be there, and that can be provided with a station which is known as a base station, or it can be without a base station. That means there is no central control to all the stations within the region. So if that central control is there by a station which is known as a base station, some access point, and this base station is also known as an access point. Okay, whereas with the sometimes we don't have any base station, and all the stations within the region, they have to manage themselves. Okay, now even this the wireless LANs, they are designed on the basis of the Ethernet. Okay, and as we know that what protocol is used in the Ethernet? CSMA-CD. Okay, but in case of wireless LAN, the CSMA-CD cannot be used. Can you tell me why? What can be the reason? They cannot use this CSMA-CD for the wireless LAN. As we know that before transmitting, a station would sense the channel. That is what it does in CSMA-CD, isn't it? But in case of wired network, when the frame is sent, when it is transmitting, meanwhile it is also listening to the channel to see whether their collision has been occurred or not. But in case of wireless LAN, while it is transmitting, okay, meanwhile it cannot sense at the same time. Are you getting this? Because a certain frequency because it is transmitting through the air, certain frequency it is utilizing for transmission. But at the same frequency, it cannot receive it. Are you able to get my point? Hello, isn't it? While it is transmitting, it cannot listen because it is using certain band of frequency for transmitting through the air, or some radio transmission is carried out. For that, it uses certain frequency, and at the same frequency, you cannot receive, you cannot perform the transmission as well as receiving at the same frequency, isn't it? So that is the problem with this wireless LAN. No doubt they wanted to uh, adhere to the same, I mean, same standards as it uses in the Ethernet. But here, this would be the this is one of the problem, that they cannot use the CSMA CD. What can be the other problem which it faces in this wireless LAN? What can be the other problem? Have we learnt about the hidden station and exposed station problem? In the last lecture, I had already explained you about MACA, MECA, and MECA-W protocol. In case of, we'll see what is this hidden station problem or exposed station problem. Okay. Say suppose C wants to send some data to the station B. Okay. And meanwhile, A also wants to send some data to station B. And the range of C is in this circle. Are you getting this? So before A wants to transmit, it would sense the channel. But since it is not in the province of C, it would not come to know that the channel is busy. Are you getting my point? You can see that this is the range. This gray part, the shaded part shows the range of C. And B is within the range of C. And B is also within the range of A. Okay, you can see that there is the range of A is something like this. All the stations which are in this area, they can sense this station A. So what happens here? When C is sending some data to B, meanwhile, when even A wants to transmit some data to B, so A would sense the channel and it finds that the channel is free. No one is transmitting anything in its region. So what it will do, it will also start transmitting. Okay, and here there would be a collision. Do you agree to this, all of you? Okay, so this type of problem is known as a hidden station problem. Hello. Okay, so now assume that the next type of problem what it faces is the exposed station problem. In case of exposed station problem, A is transmitting, A wants to transmit some data to some station, say suppose D, which is in its range. Okay, and B also wants to transmit some data to station C. Now, when B senses the channel, it will find that the channel is busy, but actually it would have sent without any problem to station C, isn't it? Because C is not in the range of A. Okay, so this type of problem is known as a exposed station problem. Fine. So this type of problem, like hidden station, exposed station, as well as it cannot use the CSMA CD, isn't it? And we have come with the solution of this also, that we have that we'll see as we go further. And the 802.11 standard, okay, it supports two modes of operation. There are two modes of operation. One is known as a distributed coordination function, DCF. That is nothing but distributed coordination function, and the other one is point coordination function, that is PCF. P stands for point coordination function. Okay, so there are two modes of operation. One is known as a distributed coordination function, the other one is known as a point coordination function. So by the name itself, you can make out that this is distributed. That means it is not central. Okay, whereas in the point coordination function, it uses a base station. Okay, that means there is some station which would take care of the host or the stations which are in its own region. Fine. Now, all the implementations, it must support this DCF, but the PCF is optional. Some implementation may support this PCF or some may not support, but it is compulsory that all the implementation should support this DCF. Right? Now, this DCF would use CSMA CA. So we have learnt about this CSMA CA. Okay. So in this CSMA, that means carrier sense multiple access with collision avoidance. We have learnt about this, isn't it? It uses DCF uses the CSMA CA, and here uh, sorry. Okay, when a station wants in CSMA what happens when a station wants to transmit, it first senses the channel. In case if the channel is busy, it has to wait. Okay, and if the channel is free, it can start transmitting through that channel. Say suppose if a collision has occurred, then it has to wait for certain random period, isn't it? And once again it has to try, and as we know that how much time it has to wait, it depends upon the binary exponential back of algorithm. So we have studied about the slots. For two slots it would first time it would wait for one slot, then it would wait for two slots, then it would wait for four slots, and so on. As the number of collision increases, the slots for which it has to wait to transmit through the channel should be increased, isn't it? That we have already studied. The other mode of is that it can use this MACAW. That means multiple access with collision avoidance for the wireless network. In that, it uses this RTS and CTS. So we have studied about this. What to overcome this hidden station and exposed station problem up to some extent, they can send this RTS as well as CTS. What is this RTS and CTS? Hello. RTS stands for request to send, and CTS stands for clear to send. Okay. So say suppose station B wants to send some data to station C. Okay. So before actual transmission is of the data is carried out, it would send us frame which is known as a RTS, that is request to send. Okay. Now this RTS is sensed by station A because it is in this region. Are you getting my point? Okay. And RTS would also be sensed by station C also. Fine. Now, in response to this RTS, CTS would also send a signal which is known as a CTS, that is clear to send. And any station which are in this range of this station C, say suppose station D is here. Okay. Station D may not get this RTS which is sent by say suppose station A is sending RTS, but station D, since it is not in the range of A, it would not sense this RTS signal by this station A. But since it is in the range of C, it would come to know that some other station is already using the channel, and if it wants to transmit, it has to wait till the channel becomes free. Is this thing clear? Okay. So up to some extent, this hidden station, exposed station problem can be overcome by this RTS, that is request to send as well as clear to send signal. Followed? So now say suppose, I'll take one example. Say A wants to send some data to station B. Okay. And this can be it would send an RTS signal to B, and this RTS signal would also be sensed by station C. But the RTS signal would not be sensed by station D, which is away from A, but which is nearer to B, isn't it? Now, in this RTS signal, it also contains the time up to what extent of time it would use this channel. Okay. And meanwhile, B would also send a CTS signal, which all again this also contains certain time up to up to how much time it would use the channel, or the channel is occupied. When the CTS signal is sent, that would also be sensed by station D, and by looking at the CTS, it would come to know up to how much time it has to wait. Are you getting this? It is not just a signal, but it also provides the time up to what extent this channel would be occupied. Fine. So you can see that station A is sending the RTS signal. Okay. In response to that, you can see that here uh, the B sends the clear to send signal in response to this RTS signal. Now C station, it hears this RTS because it is in the range of A. So what happens, it would start a timer which is known as a network allocation vector. And as I said, this RTS CTS signal contains the time up to what extent the network would be busy. Okay. So when C hears this RTS, it would start some timer within itself, and that time is known as the network allocation vector. Okay. And when the CTS is received by the station D, you can see that D is nearer to station B, and station B is sending the CTS, which has that timing information. So when the CTS is received by station D, because station D is not receiving this RTS, it cannot hear this RTS, but it is able to hear this CTS. So what it will do, even that one more timer within itself, it would start, and that is again known as a network allocation vector. Okay, so this timer would be the time for the RTS signal, CTS signal, the time for the data which it would send, and the acknowledgement. So up to this extent, the timer would be started by these stations, station C as well as station D. And this is also known as a virtual channel. Okay. The station C, station D, since it uses this timer, or and it would not use this channel, and hence it is known as a virtual channel. And these are known as they are using this physical channel, and hence it is known as a physical channel. Hope you are getting this. Any doubts in this? Okay. What is use of the timers? If the timer is not used, again, suppose RTS is sensed, CTS is sensed, and say suppose while data is transmitting, what this station D say, assume that station D, because A is transmitting the data and D cannot sense that data by the it cannot sense the channel. It will find that the channel is free, isn't it? And if it may start transmitting at the same time, there would be collision. Yes or no? You can see that A is transmitting the data, isn't it? But D cannot sense it because it is away from A. And meanwhile, even it starts transmitting to B, then there would be a collision or not? So instead, since due to the timing information which is sent by in this RTS CTS frame, so by using this, it would come to know that the channel would be busy up to certain time, and it would maintain a timer. Each host can maintain a timer within itself. It is not broadcasting, or it is not telling others that we are waiting for that. It is just for themselves to wait for the channel, for this communication to be completed up to this acknowledgement signal. And once it has been finished, then it can start once again that RTS, CTS, etc. Hope everyone is clear with this. Hello. Fine. Now, say suppose, Priyank, is this clear? Why it maintains this timer within itself? Okay. Say suppose The wireless channel itself, they are noisy and unreliable. Okay, because wired networks are more reliable and they are usually the noise free, but the wireless networks, due to the atmospheric turbulence or um, uh, even they are not reliable because anyone can tap or anyone can receive the signals, isn't it? So in case even some of the frequency bands can also be used for day to day use. For example, even the microwave oven what we are using, they it uses certain frequency of the signal, and it may interfere with the radio frequencies through which the data communication is carried out. Okay, so in case, say suppose if the probability of bit to be erroneous, let if we assume that it is p, okay, and the error free bit is 1 minus p, isn't it? If this is the error, the probability of the error, then the probability for the successful of the bit to be transmitted is 1 minus p. In case if we are having n bit frame, assume that if I'm having an ethernet frame, what is the size of the ethernet frame? I think it is 12,144 bits. Okay, now to see that the entire frame is received without error, then it would be 1 minus p raised to n. Are you getting this? Entire frame, we are not concerned only with a single bit. In case if we want to have the entire frame to be error free, then it would be 1 minus p raised to n. Okay, say suppose if the probability of error is 10 raised to minus 4, if the probability of error is 10 raised to minus 4, and if we are having an ethernet frame whose size is 12144 bits, then 1 minus 10 raised to minus 4 raised to 12144 bits. So this would be approximately equal to, that means it is less than 30%. That means the probability of successful transmission of the frame or correctly is around it is less than 30%, even if a single bit error is there among this 12144 bit. Okay, so to instead of having a bigger sized frame, it can be divided into smaller sized, to reduce the probability of erroneous frames. It is divided into a fragments. You can see that the frame is divided into a number of fragments. You know what is the fragment, isn't it? So what happens, the entire frame is divided into a smaller pieces which are known as the fragments. So the station A would divide that frame into the fragments. So fragment 1 is sent, the acknowledgement of that would be sent to the by the station B to the station A, then the next fragment would be sent, and so on. Okay, and the timer for this NAV would be started by the station C as well as a station D. So one advantage of fragmenting is that the possibility of error would be reduced, as we have discussed. Even if a single bit error is there whose probability is 10 raised to minus 4, then to the possibility of successful transmission is less than 30%, isn't it? So as the size of the frame is small, the possibility of successful transmission would be more, and hence the frame would be divided into number of fragments. Followed? So now uh, for every fragment, an acknowledgement signal would be sent. Followed? And here, in case if there is some error in only a single fragment, say suppose fragment 2 has been corrupted, then it is not necessary that the entire frame, all the fragments of the frame has to be sent. Only that particular fragment which has been erroneous, only that fragment, part of that fragment should be resent by the sender. Okay, so like this, the throughput can also be increased. Follow? So this is about the DCF mode. So in the next class, we'll see about the point coordination function mode. Okay. So till now we have studied about the DCF, that is the distributed coordination function. And next we'll see about the point coordination function. Any doubts in this? Hello? Any doubts from any of this part, whatever is taught to you? So we'll stop here and we'll continue in the next lecture.